In this video, I would like to demonstrate to you the concepts on arrays and demonstrate how arrays work in memory. So in order to just get the basics of arrays right, I'm going to create a variable, just a normal integer variable that I'll call x. And what I want to demonstrate to you is that this integer x has an address and also it has a value, so percentage d x. We can print out the value. Let's set the value equal to 5, and we can also print out the address. Now in the slide you will see it's printed out as percentage b. I'm just going to print it out as percentage d because in essence the address is only a number. It's just it's a place in memory where your variable resides, so it's just a number. So I'm going to print out the address of x and x as two separate numbers in then and new line. There we go. And this should print out the address of x and then its value, which should be equal to 5. Just going to do this. So what you can see there is the address is 2686748. The value is 5. So if I change my code to percentage p, it'll look different. And that's how the slides show it. It's just printed out as what we call a hexadecimal number. But you don't need to worry about it. It's just a number and it uses base 16 rather than base 10. But you don't need to understand that. So just run that again. You can see that's the address of x, that's the value of x. So I'm just going to put x colon all of that. Okay, so now what that means in memory is that that in terms of the memory, at some location in memory, if this is our whole memory block, somewhere here we have a location where x is stored. So the name of this variable is x and its address, as we saw from the code there, its address is equal to 2686748. So we have a variable here with that address, and I'm just going to change the resolution here so it looks a bit better. In fact, this has stopped working, so I'm just going to stop quickly. That's a lot better. So there you can see we have some variable, its name is x, its address is that, and this variable has a value, and the value that we've given it is equal to 5. So what I want to demonstrate to you now is what happens when we declare arrays. So let's declare an array. It's an integer array, which means the values inside this array will be of type integer. Let's call the array y, why not? And this thing we're going to make an integer array of 4 elements. So we're saying give us an integer array, its name is y, and it has 4 elements inside it. If I now do the same for y, so all I want to see is I want to see what has happened in the background here. What has C given me? Let's print out exactly the same for that. So now I'm just going to say y, and its address will be the address of y, and its value will be the value of y. Okay, let's just see what this does. What you can see is the address of y is 2686732, which is, if you compare it to that there, it's, what's that, 16 bytes away. The difference between those two numbers are 16 bytes. The value of y, remember y is the name of our array, the value of y is also equal to the address. And that's just something that's weird about C. It just does that. The name of the array is the address of that array. So what I'm going to do, I'm just going to swap these two around, because C assigns memory in the reverse order in this case. So let's just do that. And what you can see now is X lives at 32 and Y starts at 36. So X is 4 bytes because it's an integer. Y is 4 times 4 bytes is equal to 16 bytes because it's 4 times 4 integers. So in that bunch of integers called Y, we use 16 bytes. So you can see there's a difference of 4 bytes there. So the first 4 bytes are consumed by X, and the next is consumed by Y. And I'll quickly show you what that does as well. So just to go back to our memory concept, that means that X now resides at 32, 6732, and then we have something called Y. Its address is equal to the same, and then 36. So it starts 4 bytes on, and then its size will be, as I said, this is 4 bytes. The size of this is 16 bytes. And now the question becomes, what happens to the stuff inside here? So let's just print that out and see. So what I'm going to do is I'm just going to give these 4 elements, I'm going to give them values. So I'm going to give them value 10, 20, 30, and 40. So that's our starting values for Y. And what I'm going to do now is I'm going to print out the address of each one of them. So I'm going to put it in a for loop because we know quite a bit about for loops. And then what I'm going to do is I'm just going to generate an integer I, which will be my counter here. Alright, so I have for I that goes from 0 all the way to I less than 4, because I have 4 elements inside the array and I want to increment I in between. What I want to do is I want to print out Y %d, which will be my index, has a certain address and it has a certain value. So now I have to print out I as well, and I want to print out the address of that element. So element number I, which will go from 0 to 4, of array Y, give me its address, and then also give me the value for element I. So this should print out Y0 to Y3, each one's address and each one's value. Let's just see what that does. There we go. So what is interesting here is you can see that what it's done is the first element, element 0, is at exactly the same address as Y is here. Okay, so I'm just going to change the addresses to reflect the new updated address that it's given now. When you compile, it decides where to put stuff in memory. When I compiled with the additional I here, it decided on new addresses. So I'm just going to fix it here. So the address of X is now at something 12. The address of Y is at something 16. And then I have my 4 elements of Y. So I have Y0, that's Y0. I have Y1, I have Y2, and then I have Y3. So my 4 elements, Y0, Y1, Y2, and Y3, are slotted right after X. You can see this is X here. X, X, X. This is Y. So all 4 of these bytes are Y, and it's made up of Y0, Y1, Y2, Y3. And what you can see is from the address of Y0 is exactly that. And that makes sense. Y starts here. So its address is equal to, Y starts here. Its address is equal to 16. Y0 is at that first location, so its address is also equal to 16. Y1 its address is equal to 20. So that's address equal to 20. Y2 address is equal to 24, you can see here. And then address 3 is equal to 28. So it will be address is equal to 28. You can see it's 4 bytes in between every time because each one of these integers consumes 4 bytes. Now, what we can also see here is each one of them has a value. So before I go on, just to be clear, from this you can see that if you just use the name of an array, as we've done there with y, or if you use ampersand y, so the address of the array, or if you use the address of the first element, it gives you exactly the same thing. So they're exact equivalents. And then we said each one of these has a value that we've assigned. So in here the value is equal to 10, 20, 30, and 40. So this is what is going on in memory. Now if I do the following, if I say let's go all the way up to number 4, so that'll go from 0 to 4, you will agree that we don't really have an element number 4. Our memory that we allocated for this only caters for 4 elements, so from 0 to 3. If I now say go into element number 4 as well, you will see something strange here. What's going on here is that it's saying the value at this address, so it's now going here, which is outside of the scope of y. This here is the scope of y. It's the 4 bytes. And now we're saying go to element number 4, which does not exist. There is no such thing. And the value that it's giving me is 4. And the address is obviously address is equal to 32. It's 4 bytes on. So let's just see, just take a stab at it. If you try to see what the address of I is, so I'm going to do exactly the same here. I'm going to do it for I. Remember, I is our counter that we used. Address, value, and then of I. What you can see here is the address of I is equal to 32. That means, coincidentally, I resides at that address. So I lives here. This is I's place. This is where it lives. So its name is equal to I. So by going beyond the limits of y, we have coincidentally and erroneously gone into the memory space of I. So we've said y4, which doesn't exist, and coincidentally something else lives there. That's like going into the wrong address and finding someone else lives there. Same thing. The address of I is 32. So if we go to y4, we're going to go into I's address. And that's why when you look here, I just want to print this out again. If I do this separately, so if I do print out y4, which doesn't exist, remember, and I say print out y4, so give me the address of y4, give me the value of y4, you will see that it's exactly the same thing here. Because this doesn't exist. We're going into memory that we can't go to. Alright, so that's the one part of it. So let me just delete this. We don't really care about this. So now the question is, how do we pass this into functions? If I now want to send this into a function, so I want to send my array into a function. Let's call the function just display or something, display array. Into this function display array, I want to send y. Then I need to obviously create this function, void, and the function is called display array. Then I need to tell display array, what am I going to send you? And what I'm going to send it is an integer array, because that's the type of y. You can see here, y is an integer array. So I'm going to send it an integer array, and I'm going to call it local y, whatever you want to call it, doesn't matter. So local y will now be an array that I can use as if it's been declared locally. And that's really what's happened. The problem is now, inside this function, when I get this array, I have no idea what the size of it is. I don't know where the limits are, because all I've received, in essence, is the address. And I'll quickly explain to you why that is. When we call this function displayArray, we give it y. What you can see here is, when we printed out the value of y, it was the address of y. So what literally happens here is, the address of y is copied and pasted into, sorry I missed something, and pasted into a variable local y here. So this local y array will just contain the address of y, which is 2686716. That's the address of y. So this thing will point to y. It will contain y. So what I can do now is, inside here, I can do printf, and let's do the value of y. Let's do exactly this, but we do it for local y instead of y. Local y. Local y and local y. So all we've done is we've sent y, we've sent to a function called displayArray. The function displayArray receives that y. Remember now, y is the name of the array that just contains the address. So that address is passed into this function, which expects an array. So local y will now contain that address. So I'm just gonna what do I want to do? Oh, I just need to create the function prototype as well. So I'm making the function prototype, semicolon, and let's run it. So hopefully this should do what I expect. So what you can see here is the address of y is that, the value of y is still this. Then I passed it into the function. I called the function displayArray with that value. That value is sent into local y, and then local y, what you can see here is the address of local y is something else because it's a different variable. This is just a variable that's created in memory. So somewhere in memory, and to be precise at location 88688. So somewhere here, it's now said, let's create something called named local y. And its address is 688. The address and its value, and this is where it gets interesting, its value is equal to the address of the array. So now, local y, we call it point. Local y points to this original array here. So what I can do is here, I can do a printf, again, of all the elements. And let's not go beyond the limits anymore. And then I just use local y here. And local y. And local y. So what you can see, so what we expect to see is that this thing will print out the whole array. No, it won't. Error is detected. Oh, I've not declared I. So let's just declare I locally as well. Int I. There we go. So what happens here is from inside main, we're printing out these 10, 20, 30, and 40 with their addresses. And then from inside here, I'm printing out exactly that same things. You can see the address of local y1 is that address of that variable. So it's this local y is in fact referring, that's why we call it call by reference, it's referring to that exact same place in memory. So you can see the address of local y0 is 16, and that's exactly what we had here. The address was 16. The address of y1 was 20, 24, 28, etc. So here you can see 28, 24, 20, and the values, of course, also the same. The only thing that's different or interesting here is the address of local y is that, because it's a new variable, and its value is the address of our array y. I'm giving you more information than you need, but I want you to understand this. Alright, so now the next question is, before I say that, what we typically do, you can see here I've assumed that the size is 4. What we typically do is we just pass to the array, we just pass the size as well. So we just pass 4 to it, and then we use a variable int size. We use size rather than fix it, so that your function is configurable, and so that your function doesn't need to know the size. That should do exactly the same if it works. No, I just need to fix my prototype as well. So there we go. So it does exactly the same thing. Everything's still good. Now the thing with passing the address of the array to the function is that this function has the ability to go to that address and change values. So what I can do in here is I can go I can go local y, and then I can say local y 0 is equal to 100. And what that'll do is, I'll just talk you through it. This is go to that address and go to this index at this address. So position 0 at this address. This is called dereferencing, by the way. That says go to the address, get access to the memory at the address. The square bracket says give me access to that memory at this address. Go to element number 0, so which memory? That address plus 0, and make its value equal to 100. So what that'll in fact do is it will go into this position here. Just see which one I changed. Change 0. It'll go into this position here and change that to 100. So it physically goes into the original array and changes its value to 100. So if I do this now, if I just call this printout again, and let's do it with a 4 so it doesn't go beyond the limits. If I now run this, you will see the value here has changed to 100. So before I do the function call, it was equal to 10. After I do the function call from main, it's equal to 100. So it allows you to affect the changes. I don't think I've said this. I just want to quickly show you something as well. If I do local y 4, which is obviously beyond the limits, and I make that equal to 20, I make it something else, make it 99. If I make local y4 equal to 99, now remember local y4 is in fact the address of I, it's where I lives, not really local y. Then if I print out I again, I think I have it somewhere here, seems I've deleted it. So if I printf the value of I, this should now print out 99, because in that function I've accessed the memory and made it I. Well, in fact it's not, because it's using different memory now. Because of this I as well. Okay, so it's affecting something else and I don't know what it's affecting. So you're going into memory somewhere and it's changing that memory erroneously. Okay, the next thing I want to show you is you can also send elements of the array into a normal function. So let's just make a new function, and I'm going to call this display element. Display array display element, and what I'm going to send this is I'm going to send it one of the elements of the array. Now each one of the elements of the array is just an integer, so I'm just going to call it x for now. I'm going to take this out. So this function will expect a single element of the array, and what it'll do is it'll just print out the address and the value of that x, just to demonstrate the point. So I'm saying local x, or x, is equal to its address and its value. I'm just going to put a small note here to say from disp L, so that we know what's going on. We're printing from display element and we're not printing from main. And then I just need this function prototype as well. Here we go. And then I also need to call this from the main function. So what I'm going to do is here, I'm going to call that display element, and I'm sending to it one of the elements. So let's choose one of the elements. Let's make it y3. So you would agree that what is happening here is display element. What is happening here is I'm calling a function display element. What I'm sending to the function is a single element of this array. So that says go to the array, give me access to memory location, the third one in that block, so the third integer of all your integers. Sorry, it should be the fourth integer of all your integers, counting from 0. So element number 3, start counting from 0. Take its value and pass it to this function here. So what happens is the value of y3 is copied and pasted into a new variable x. So just going back to our memory map, somewhere memory will be allocated and given to a variable called x. And the value of, what are we copying? y3. The value of this y3 is copied and pasted into that there. When the function runs, when the function completes, it forgets about this x and deletes it. So we expect this thing to print out the value of y3 and the address of x, and that's the important thing to take here. So the address of x is now 2688, so you can see it's replaced this, it replaced this local y. The address of local y is now something else. That's actually the same, so it's, just see this quickly. So it's cleared that memory after it's called the local y function, after it's called this display array function. It's cleared that memory, and now it's using that exact same memory, the one that it's used here for local y. After the function is called, it's using that exact same memory for x temporarily. So because this local y only resides within that function, it's used temporarily, and then when the function is closed, this memory is free again, and then x uses that exact same memory. So you can see here the address of local y was that, the address of x is exactly that, and the value is 40. Why? Because we called the function, we gave it y3 as an argument, y3's value was taken, copied into wherever x resides, and x resides there just because that memory was free, the computer chose it, and the value 40 was put in there, and that's why the address of x is that, and the value is equal to 40. So the important thing to take from it is, this here is called call by reference, because we give it an address, and it goes and affects that local position, that it can affect that variable. This here is called call by value, and just the value of that element is passed, because we gave it an integer, we didn't give it an address. We didn't send an address, we sent a value. The other way to look at it is this here, the value that is sent is in fact an address. So that value is sent into this variable here. And then we can dereference this. We can use the brackets to get access to that memory locations. And that's all for arrays for now. Just want to think if I wanted to say anything else. Oh yeah, let's just do one thing else, and that is if you wanted to copy, if you wanted to make a duplicate of an array. So let's say we wanted to modify an array, and we didn't want to, or at least we wanted to create a modified copy of an array. So we wanted to send y, we want to send to a function, and we want this function to return another array, to complete a function and then have a new array printed out, for example. So the way you would do this, let's call it modify array. Modify array. We want to send y to it, and then we want it to modify the list, but not inside y. We want a new list that is modified, a modified version of y. So let's call it z. So the first thing we want to do is we want to declare a variable called z. Mind you, this will change the addresses now. It could. So I'm going to make it z. It has 4 elements, and I'm going to make all the values equal to 0 by just doing that. And now I need to, in some way, I need to call a function modify array. And let's quickly define a function modify array. Modify array, and I'm going to send to it, let's make it a, b, and c. A, int, b, and I'm going to send it the size as well. So this function of mine will receive one array reference, another array reference, both of type integer, and the size, just so that I know what the size is. So in here I will call modify array with the size. So in here, if I wanted to make a copy of it, I need to go through the whole array and make a copy of it. So int I is equal to 0 will be my counter. I need a for loop, and I want this to go up to size, which was passed here. It was not a global variable or a preprocessor directive. And in here I can do something like bi is equal to ai. So this will just copy the whole array. This will make a duplicate of the whole array and put it into Z. So let's just quickly do that, show you that it works. Make the function prototype, run it, and what you can see is this runs, nothing weird. Calls modify array, and let's print out the values of Z as well. So what we expect to see now is, after we've done this modify array thing, we should see that Z has now also changed to be exactly the same as what Y was. Because we called the function modify array, we sent it the reference Y. So it went into, it took the address of Y and sent it to this function into A. So now A's value is the address of Y. And it took the address of Z, which is another array, put it into B. So the value of B is the address of Z. And all it did was it said, go to that address, get access to memory at location I, and make it equal to whatever the array A is at location I. So Z should be exactly the same values as Y. And that's what you can see here. So Y is 100, 20, 30, 40. Z is 100, 20, 30, 40. Of course, because it's a different array, it has different addresses. What you can also do is do silly stuff, like say, and this should swap it around and revert the order. So what you can see here is all that's happened is, actually I just made a quick mistake and I can show you why and how. So this goes 100, 20, 30, 40. This goes 4, 40, 30, 20. It's obvious that I've just gone into memory that I don't own. Let's look at Y. What I've said is go to I size, which is equal to 4. Right? I've passed the size 4 to it. 4 minus 0 is 4. So I've gone into memory that I don't own. So I need to make a -1 here just to start from the right place. So that reverses the order. That says Y goes from 100, 20, 30, 40. Z goes 40, 30, 20, 100. The exact opposite reverse order. So that's copied the array but modified the new array. Didn't just copy it, it modified it. So you can do whatever you please with that. And I think that's more or less it for arrays. Oh no, sorry, there's one more thing. The other thing that I think is useful to know is you can also check the size of an array by doing something. Just going to show you this. You can check the size of any variable by saying the size of by using a function called size of, and then passing the array to the function. The variable to the function. Size of x and size of y. And what you can see here is y is obviously now an integer array, x is just an integer, but we expect this to return 16, we expect this to return 4, because it's one single integer, this is 4 integers. So it won't print out the size of the address, strangely. It tells you what is the size of the array. I just want to see what the problem is now. Oh, sorry. Percentage d, it just gives it back as an integer. And typical mistake. Right, so what you can see here is if I scroll up, the size of x is 4 and the size of y is 16. Okay, so that's a bit of an anomaly. That doesn't say what's the size of just y, because we know y is an array. It tells you the size of the array. It doesn't tell you the size of an address. Just for interest's sake, if I do that, it'll tell you the size of the address, and the address is just an integer, so that should give us 4. So the size of the address is just 4. Okay, anyway, so that gives us 4 and 16, because the one is 4 bytes, the other is 16, and what I want to demonstrate here is if you do this from within a function. So if you pass to a function, the address goes into this here, into local y, and if I printf the size of local y, you know now local y is its own address, and its value is just the address of that original y. The size of local y, this will return 4. As you can see here. So this is the size of local y is 4. Why would that be? It's because local y, as we see here, local y's address is somewhere. It's just an address. It contains what we call a pointer. It is a pointer. Its value is just an address, and that address is just an integer. So if you do this to an array that was passed into a function, if you do size of here, it'll just give you 4. Right, so you can't use the size of inside an array, and that's why we need to pass the array size here. If I declared a new array q of 4 integers here, and I print out the size of this, it should work again because it's in the right scope. C is intelligent enough to do that. Size of q. It should give me a 16 there. So what you can see is because it's in the right scope, C knows, C was declared here, yes, it's 4 integers, so its size is 16. Locally was not declared here, it is just a reference, it's just a pointer, and a pointer is just an address number which is contained of 4 bytes, it's just an integer, and its size is 4. A bit confusing, but it's useful to know.